Alright, so I told one of my viewers I would cover Einstein's field equations, and here we are. Well, actually, look, it's much simpler already. There are some prerequisites for this video, and if the words vector, derivative, dot product sounds familiar, you should be in sort of good shape. Otherwise, you should probably use your Google to look those terms up. Maybe catch up on some YouTube videos, I don't know, Khan Academy or something like that. Now, there are many videos on YouTube that covers Einstein's field equations, but usually they have a view that's a bit too narrow. So what I will try to do in this video is to tie up some loose strings, and yeah, hopefully it will make some sort of sense. Now, some tend to focus on parallel transport, where you move the vector around some loop. Others tend to focus on how parallel lines converge or diverge as you move across some wrinkly surface. But that's sort of just another way of stating the parallel transport thingy. Others seem to think that it's all about matrices, but they are clearly lacking the difference between a tensor and its matrix representation. And we won't go into all that much detail on the subtleties right there, but there is a clear distinction. So now, what is it about? Well, it's an equation that relates the shape of a space-time to the energy and momentum that is within that space-time. And this is done in such a way that doesn't depend on the parametrization, and it's also made so that it fits observations, but we'll get back to that later. Because we will start off with how you go about creating such a surface that does not depend on your parametrization. And what do I mean with parametrization? Well, take something like the unit circle in x, y coordinates with equation. So you have x squared plus y squared is equal to 1. So this is the equation for a unit circle. One parametrization in terms of the parameters x and y is x equals the cosine. Well, we need some new parameter, let's call it theta. And y would be the sine of theta. Another one, let's see, that will be something like, for y you get, q divided by 1 plus t. Now, both of these parametrizations perfectly describes the unit circle in terms of t or theta. So back in 1820, 30 something, Carl Friedrich Gauss, I think I botched the pronunciation, but still, he was investigating a surface in terms of x, y, c coordinates that depended on a u and a v component. I'm just drawing out some generic surface right there. Hopefully that makes sense. And yeah, an equation speak. This would be something like now in modern speak we would call this a vector valued function. So R gets this cool little arrow hat. That way we know it's a vector that has an x, y and a c component. Now Gauss wanted to know what components of this surface is unchanged if we were to like fold it, like wrinkle it about without stretching it or tearing it apart? And some of the more obvious ones are something like the length of a line. So if you had some kind of line that was sitting in this UV plane, then no matter what I were to do, as long as this thing is not stretching, the length of that line will not change. And sort of by extrapolation from that, you could also think that if you have some angle between two lines, well, that angle shouldn't really change. If you had a piece of cloth and you were to draw a cross on it, it would still be the same cross regardless of how you were to warp that shape. Now, since length don't change and angles don't change, you can also sort of extrapolate that. If you had some area in this surface, that will also remain unchanged. And we will do the derivation for length and leave the other one as an exercise, because actually we don't really care about these things right now. We care about a curious object that pops out of this derivation. So let's say that our u and v component is dependent on some new variable, and we're going to use t. Then this will trace out some curve in our surface. And if we imagine that this thing was made up of segments that had the length delta t naught, delta t1, delta t2, and so on, so on, so on, then the change in R with respect to the change in t that would simply give you the rate of change from one point to another. And if you were to multiply this with the change in t, well, then you would have the length of each of these segments. And if you want the length all the way from, let's say this was the starting point A, and this was our end point B, well, then you could just sum up all of these segments, and we'll do this with summation from A to B. So now we're just going to do some infinitesimal trickery right now. First off, let's swap these out for some infinitesimals. So now we have the derivative of R with respect to t, and summation, because we don't want a jagged line, we want the smooth curve. So we turn this whole thing into an integral. Ooh, how neat. Alright, so oh, I also forgot one thing. The derivative can go negative. We only care about length. And since this is a vector quantity, we actually need to take the norm. Oh, yeah, we should probably give this a name. This is equal all this is equal to S. Now, since norm is sort of the absolute value of a vector quantity, we could rewrite this whole thing as now a bit of magic. Now, you may not be familiar with partial derivatives, unless you had a multivariable calculus course. But if we for a second imagine that R is a function, a composite function of the function gt, and then you may remember that the chain rule gives the derivative of this with respect to t as the derivative of r with respect to the derivative of g, the derivative of g with respect to t. And now if we were to square both sides, then you could distribute out the square. So this thing could be rewritten as alright. Now we have this derivative square thing underneath there, and we're sort of going to do the same thing, but because it's partial derivatives we will get a binomial. So another way we could write this thing underneath there, let me just clear up the board a bit, because this is going to look quite messy. But yeah, I'm going to rewrite this and it's not going to look pretty, but we could say that this is equal to now I'm running out of room, so I'm just going to continue right over there. Let's see, the final term is so now I know this looks a bit messy, but this is still an arc length S. The square root is continuing all the way over there. I ran out of room, but we will manage. I know this looks, that's plus, that's plus. I know this looks a bit messy. I know this looks quite messy indeed. But we are going to group some terms, or we're going to relabel them. So let's just relabel this thing E. We're going to relabel, let's see if we can list these ones. So we're going to relabel these as F, And finally, we're going to relabel this thing as G. So now we can rewrite this entire arc length expression as now this is still our arc length. You may recognize it as a quadratic that you've expanded out, and you have this standard squared term, mixed term, and second squared term. So now the thing that actually governs the behavior is this integrand under the square root. So if we were to differentiate both sides, well, then we get to remove the integral. This is called the line element. And if we take the square of the line element, we also get to remove the square root. Now this quadratic differential that we got right here is called the first fundamental form of the surface, and it actually completely describes our surface. And since we already have some coordinate system, we can write this first fundamental form in matrix notation as pretty neat, huh? Now, some of you may already have jumped ahead of me and assumed that this is the metric tensor. You are sort of right, but it's the matrix representation. I'm not really sure if I'm going to go all that deep into tensor products and one forms. But or should we? Wait a second, let me have a think about it. No, we will not. But we will try to show its usefulness with an example. So let me just, let's say that we have some tangent vector a hat at the point A, and we have another tangent vector B arrow hat at B. Now let's say that we wanted to measure the angle between A and B. Usually we would perhaps do something like a dot product, and that's exactly what we're going to do. So now remember that any tangent line, so the tangent line A could be written as and similarly for B we have I'm not going to do the complete derivation, but the terms that end up mixing ends up being the terms that are E, F and G in such a way that you would end up with form. If you wanted to write this in matrix form, I'm running a bit out of space. This is the same as. And once again, we see, just as with the fundamental form, we see that the dot product is also summarized by this matrix. Now, we see that this is sort of just a function that takes in as its argument an A vector and a B vector. So, we could just write this as so now we have this function g that takes as its arguments A and B, and it will output some scalar number, as this is just the dot product. The t right here is it's the transpose of B, so that we turn the row into a column vector. And this thing right here is the metric tensor. Now, what actually makes this a tensor is the way that it transforms under the Jacobian. But yeah, we're going to skip that for this video. And instead we're just going to have a look at some properties and uses of this metric tensor. So, for starters, one important property is the fact that it's symmetric. And we can also use it to calculate the length of a tangent vector, simply by taking so the norm or length of a tangent vector is the square root of the metric tensor of a vector with itself, and we can also calculate the angle so the cosine of the angle will be the metric tensor of A and B divided by the norm of A and the norm multiplied by the norm of B. Now, before we cover the last property of the metric tensor that we will talk about, we need to talk about coordinates and bases. Now, so far I've labelled our axes x, y and z. Now, for convenience, I'm going to relabel them as x1, x, that's supposed to be a 2, and x3. Now, these are Cartesian coordinates, but you could have many other kinds of coordinates, and some of them are quite important for various solutions to Einstein's field equation. And for now, let's just say that these arrows also represent our bases, but you could have another basis, so you could stretch out every single one of these, or you could rotate it. It would still be a Cartesian coordinate system, as long as they all transform along the same transformation. So now, if we say that these represent the basis vectors, x1, x2, x3, and we have so these define a basis for a coordinate system. Another word for it is a frame, so let's use F. So F is the frame of our coordinate system. So now the way that we could represent the components of our metric tensor in the frame of F is by a metric tensor of xi and xj. So now imagine this is f. If we were to imagine some other basis, I don't know, something like that. Then there is some function that takes f to f, and we do this by some matrix, let's call it A, such that f prime is equal to f A. And we will require that A is invertible and that it has the same number of basis component in each direction. Now, in that case, G has the neat little property that it goes now. What we see right here is that the metric tensor, if we were to do a change of the basis on the metric tensor, then it changes along with the transformation matrix, and we would then say that the metric tensor is covariant, so it changes along with a change in basis. And now if you had the inverse of the metric tensor, then it would transform as now see that the inverse of the components of the metric tensor transforms by the inverse of the transformation matrix and is thus said to be contravariant. So it changes contrary to a change in basis. Now, these things are important to keep in mind when you're talking about changing your frame of reference, which is sort of the important thing to think about in Einstein's field equations. So far, we've only talked about linear coordinates, and our basis has been the same all the way throughout. But if you were some kind of ant or something crawling along this surface, you can only tell that it looks flat locally. So you can only tell that, well, it goes straight ahead in this direction and this direction, but globally you're not sure what the surface does. So now imagine that the UV plane is actually flat, and instead it's our coordinate that are curving. But now we have the situation that if we were to move around in the UV plane, then our coordinate axes will change continuously. So we have a sense of a change in basis. Now we know that the metric tensor changes along with the change in basis, and it summarizes all the properties, characteristics of the surface. So what if we had associated to every point in our surface a metric tensor? Well, then we have the thing that is known as a manifold. And now we will actually just forget about the initial parametric surface, and we shall instead from here on out only focus on the manifolds themselves. Let's say that we have this manifold, and we'll call it M. And on the tangent space, this manifold, let me see, let's just draw something like this is supposed to be a tangent space at the point P. So this is then the tangent space at P. That's supposed to be a T. Now, I'm not really going to go into detail why, but if every point along this manifold on its tangent space has a first fundamental form, and if those have eigenvalues that are only positive, it's called positively definite, then we have what is known as a Riemannian manifold. You could generalize it a bit and have a pseudo-Riemannian manifold. And if you have a Lorentzian manifold, you will have a manifold that satisfies Lorentzian transformations. You may have heard of those from special relativity. And if you narrow it down even more, you could get something that's called an Einstein manifold. That would be a solution to this equation. But now, let's move on a bit. Now, so far, we've kept things pretty formal, but we're going to loosen up a bit. And the thing we want to talk about is how do we quantify curvature in these kinds of manifold. Now, the usual approach has a hat. It's also some kind of manifold, and the usual way to introduce this concept is by parallel transport. So imagine that you have some vector and you move it around a loop on this manifold and back to where it started. Notice that we started off in this direction, that's changed to this direction. Whereas if I were to do the same experiment on a flat manifold, then I'm still pointing in the same direction. So we can infer some kind of curvature by looking at this process of parallel transport of a vector around some loop. So now, how would we go about describing this? Well, we need to look at how the tangent space changes when you move from one point to another point. And the thing that takes one tangent space and transforms it into another is known as a connection. And we use this del symbol to represent a connection. And if the metric takes the same equation at both of these points, then we would call this a Levi-Civita connection. There's also a requirement of it being torsion free, but we will assume that the pair of tangent vectors u and v are coordinate vectors, and so we don't really have to think about that. And now we're ready for the Riemann curvature tensor. So now imagine that we have some vector, let's call it w, and we want to parallel transport it along u and then v. But we could have also gone v first and then u. Now, if parallel transporting v along this direction does not leave the same as doing it the other way, then this quantity right here, it's the Riemann curvature tensor. for the vector VW. Now, how will we write this a bit more formally? Well, we will write it in terms of the Levi-Civita connection, and we'll write it as so now we have that Riemann curvature tensor satisfies this relationship where we have that V is first acted upon by the Levi-Civita connection for V and then U, and we subtract the same thing but we have swapped around the order of operation. So in essence what this thing does, it measures the commutativity of the Levi-Civita connection, or the covariant derivative as it's also known. Now, before we move on with the Riemann curvature tensor, I have to introduce some tensor index notation. I should probably have done it while we were doing the metric tensor, but remember that the metric components of the metric tensor was written like this. Now, the inverse should have been written like this. So these are not exponents, these are superscripts, and they indicate that this is now the contra variant component of the metric tensor, and this is the covariant components of the metric tensor. So just think about it as subscripts are covariant, superscripts are contravariant. So now let's write the Riemann curvature tensor in terms of its components. And you may not like it because it doesn't really look that pretty, but we've gone through a lot of things that doesn't really look all that pretty. So we have now you may ask, why did I put it into this form? Well, because the thing is that if we let A and B go over the same index, let's just call it C, we have now done what is known as contraction, and this expression that we have right here, well, this is actually known as the Ricci tensor, or the Ricci curvature tensor, and it's written and the observant eye may even recognize that this thing is indeed the thing that we see right here, and it's the first term of Einstein's field equation, and we can feel pretty pleased about ourselves. Neat. So now, how would we go about interpreting this thing? Well, the common way to think about it is, imagine that you have some cone in Euclidean n space along some vector. Let's call that vector G. Now, if we did the same thing in our manifold, and it turns out that this Ricci tensor is positive, then the volume of this cone would be smaller than in ordinary Euclidean space. And if it turns out to be negative, then the volume will be greater than in ordinary Euclidean space. And if it turns out to be 0, you can probably extrapolate that the volume will be the same. Now, the Ricci tensor is also key to understanding the other R in Einstein's field equation, the one with no subscripts. And if you were to take the elements of this matrix that goes along the diagonal and add them up, then you get this number, known as the Ricci scalar or curvature scalar. And the best way to think about that, if you had a ball in standard Euclidean space, then in our manifold, if it turns out that the Ricci scalar is positive, then that same ball would have a smaller volume. And similarly, if it turns out that the Ricci scalar is negative, then it would have a larger volume. Pretty simple. And now we've pretty much covered every term on the left hand side. We have the Ricci curvature tensor, it talked about the volume of a cone. We have the Ricci scalar, it talks about the volume of a ball, so it doesn't care about the direction. But it needs a metric tensor in order to exist at all. And the 1/2 in front of it is just to put it at the same scale as the Ricci curvature tensor. Now 8 pi g, the gravitational constant, speed of light to the 4th power. Now, if you look at that, all of these are just constants, and they just exist in order to get things into the units we want them to. There's also a bit of it that exists. You could talk about the weak limit approximations, then all of this would just turn into Newton's equations for gravity. And this final part is known as the stress energy or stress momentum tensor, and it summarizes all the energy and momentum that exists inside of this system. Now we will go a bit deeper into this one. So now the stress energy tensor can be represented by a matrix. And you could sort of think of it as the youth component with constant x, v coordinate. Now the various elements has various interpretations. So first off, we would talk about the 0, 0, which is the density of relativistic mass. Of linear momentum components. The elements along the diagonal we usually refer to as pressure. And the remaining components we would refer to as the shear stresses. And to give a sort of visual representation of these, imagine that we have some surface. And the density is simply the density of elements inside of this surface. And the linear momentum components is just the amount of momentum that is within that surface. And the pressure is just the forces acting into or out of the surface. And the remaining components is simply the shear stresses. So any kind of action that goes across the surface. So just think of sharing transformations if you're familiar with those. But this is all the forms of energy and momentum that you can find inside of your system. We could have delved a lot deeper into this thing. And if you want the sort of introduction to it, I would recommend looking up the Cauchy stress tensor. But usually when you go about solving this thing, you would go for something that is known as a vacuum solution. At least if you talk about an exact solution. And we will have a look at those. And in that case, every element of this thing is zero, so all of this side is simply zero. So we're just solving for whatever relationship on the left hand side that will have these cancel out. So now, if we wanted to talk about the solution to Einstein's field equation, what are we actually doing? Well, we're trying to find a metric tensor that will satisfy whatever relationship we have set up. So we know some properties about whatever is inside a stress energy tensor. Usually when you're trying to find a solution, you put this entire right hand side to zero. As mentioned, it's called a vacuum solution because there's nothing in your space. Now there could be like one thing, but there's nothing else, like a Schwarzschild solution, but we'll get back to that. So now the simplest solution you can find that satisfy that this side cancels out and becomes zero is known as the Minkowski metric. Now we can write the Minkowski metric as... I haven't really talked about the metric signature, that's why we have this minus in front. And I'm not going to bother either because we seriously need to move on. But you can sort of see that, yeah, nothing much is going on there. And this is the metric for flat space-time. And it would simply be the same as the Euclidean distance. Yeah, I'm not going to bother putting anything in and show that it actually cancels out. It's pretty long and tedious. Well, not too long and tedious. But we will move on to something a bit more interesting. Now, if we consider that, well, the Minkowski metric was all ones on the diagonal, what if we could construct something that sort of emulates that idea? So we only have elements along the diagonal. We have something that is spherically symmetric. Then, if we have the coordinates, then we can write out another solution to Einstein's field equation, known as the Schwarzschild metric. In its matrix form, it will look like now, what we have here is the metric for a non-rotational, non-charged black hole with the mass big M, and G is just a gravitational constant, C is just the speed of light, and R is the distance you're removed from the black hole within the manifold. So this thing will warp around. And now you can see how this sort of emulates the Minkowski metric. If you were to let R go to infinity, that you're infinitely removed from the black hole, we just get 1, 1. And if you have been using the same coordinate system for the Minkowski metric, well, this would be just the Minkowski metric. Now, there's some curiosities that happens within this metric. For starters, if you were to, well, let R go to 0, this thing blows up, and we have what is known as a singularity. Also, take note that this is the inverse, so it's actually 1 over whatever is inside the brackets. So you can also see that we have another infinity when we let RC squared approach 2gm. and that is known as the event horizon. Now, you could swap around your coordinates and actually remove that singularity. That would be Eddington-Finkelton coordinates. Yes. So it's not a true singularity, unlike this thing that is a true singularity. Now that pretty much summarizes what I want to cover about the Einstein field equation. Now there are many other solutions, exact solutions to Einstein's field equation. Then you have numerical methods that can approximate various situations. There's also some pretty interesting solutions where the stress energy tensor is non-zero. For instance, Wahlquist is a pretty interesting one, Bonner beams, but those will have to wait for another video. If there's any questions, feel free to put a question down in the comment section and I'll try to answer them as best I can. Yeah, maybe we'll go into some derivation of various metrics and maybe look into some interesting situations in future videos. But for now, thanks for watching and keep it interesting. Where we have this function last the components of the metric trend. You couldn't really tell if the curve. So we take the. So now I haven't really talked about metrics.